In this section, we're going to be talking about forces, which is really just different types of pushes and pulls. So one of the first things we should talk about is how forces have to act between two objects. Between two objects. So let's make up an example where it's my finger and the paper. Like my finger can press on the paper. But that also means that the paper is going to be pushing back on my finger, right? I push down on the paper and the paper is going to push back up on me. So for it to be a force, you should be able to identify the two objects that are interacting. Take gravity, for example. The Earth's gravity is pulling me down, so then the two objects would be me and the Earth. And how about I just introduce Newton's third law right now? Forces act in pairs between these objects. And they will do so in an equal and opposite way. So in the case of my fingertip and the paper, those are going to be my two objects. What we could imagine is that my finger would be pressing down on the paper. And you can draw that arrow anywhere. You could draw it starting here and going downwards. How about I just draw it off to the side right now? So the finger will press downwards on the paper. And what Newton's third law says is if this is happening, there has to be an equal and opposite force that's also happening. Forces have to occur in pairs. So then the paired force would be the paper pressing upward on the finger. So both of these forces have to happen at the exact same time in exactly opposite directions and in exactly equal amounts of force. Otherwise, you're going to break physics as we know it, which might be fun. You get a Nobel Prize. Anywho, to indicate that these two arrows are equal, one thing we could do is put two little hash marks on them. You don't have to do that. I just like to do it. It kind of gives me a visual reminder that yes, those two arrows are equal. So what we've done so far, forces are pushes or pulls. A force has to kind of occur as an interaction between two objects, and you should be able to name them. And when that force does happen, it has to happen as part of a pair. And a lot of times we might choose to ignore one of them and just focus on the other one. But they do occur as pairs. Another thing to mention is that all forces are vectors. Meaning that they have an amount and a direction. The direction might be something like right, or even just forward, or 30 degrees above a horizontal. Just describe a direction somehow if you're asked to give a force. For the amount, the units that you guys are going to be most familiar with is pounds, but that's not what we use in physics. Our SI unit for force is going to be newtons. And if you wanted a conversion, 1 pound is equal to 4.45 newtons. Just for scale, to get used to it, somebody who weighs 150 pounds and convert that to SI in newtons, 1 pound would equal to 4.45 newtons. Pounds cancel. 667.5 but this was accurate to 2, maybe 3 sig figs. Let's just go with 2, it's safer. So let's round this to 2 sig figs and say 670. Let's go back to these arrows and remind ourselves that arrows, vectors, can be picked up and redrawn anywhere we choose to. So what we tend to do in physics is pick up the arrow and redraw it on top of the object that is feeling it. So let me redraw this, kind of redrawing those arrows on top of their objects. So the finger was pressing down on the paper, so I might draw a dot here, just representing the paper. And here's the force that it feels downwards, acting on it. And we could label that a force down, or a push down, or a press down. It's all just different ways of saying the same thing. And see how I said on paper? That's kind of the object that's receiving the force, that's feeling it. So that's why this arrow started from the dot that represents the paper. So if this is my fingertip is going to feel a force upwards from the paper, not letting my finger go through the paper. And so that would be the paper pressing up on my finger. Right, on my finger. So the force is drawn, acting on that object, touching that object that's going to feel it. Let's imagine a box sitting on a floor, and how about we even just say that the floor is ice right now, so we can ignore friction. And then I'll imagine one person standing over here, pushing on it, and then another person standing over here, pushing on it. Let's presume that this person is pushing with 50 newtons of force. And how about we call this person A, and we can call the block B, and we'll say that this person is C. Hey, for crystal. So then A pushes on B with 50 newtons, which means by Newton's third law that the box B pushes back on that person with 50 newtons. So we're looking at the interaction between those two objects. Now let's look at the interaction between these two objects. So person C, crystal, might be pushing on the box with 60 newtons. What that means then is the box is also going to be pushing back on me with 60 newtons, just by Newton's third law. So we've identified these pushes between these three objects. I'm ignoring the floor right now. Let's pick those arrows up and redraw them on top of the objects. So person A, and I'm going to separate them a bit so my figure doesn't get too crowded while I'm drawing all these arrows. Alright, so the box is going to get pushed with 50 newtons. So the box feels a 50 newton push this way. The box pushes on the person with 50 newtons. And that is just from Newton's third law. The person pushes on the box pushes on the person. This person is pushing on the box this way. So I can pick this arrow up and I could draw it here, pushing left on the side of the box. But tradition for physics is to actually just kind of copy and paste it here. They both work. This is just tradition and what I will end up doing most of the time. And then the box pushes back on me with 60 newtons. So let's say we don't care about what the forces are doing to the people. We only care what happens to the box. So now let's just look at the box. Let's find the total, or the net, of these two forces acting on the box. So there's two ways you can do that. You can do it as drawing the arrows tip to tail, or you can do it by adding components. So let's pick these up and add them tip to tail. It doesn't matter which order you do them in. I've got the blue marker in my hand, so I'll do that one first. So I'll pick a starting point. I would draw 60 newtons acting to the left. From that, where that one ended, I would start to draw the other one of 50 newtons. Now the net, your answer, the sum, is going to be an arrow that goes from the very, very beginning to where you ended at. Just to not write over my own writing here again, I'll draw it right down here. So this would be your net force. All right, I'm going to take a second and define a positive direction. How about we do the default to the right? So wouldn't this one be a positive 50 newtons along the x direction? And then this one is pointing backwards compared to that positive x direction, so we would call it a negative 60 newtons. So we could add up the amount of force in the x direction from the red force, and we could add it to the amount of force in the x direction from the blue force. And that would give us our net, our total, along that x direction. We had said that this we could call a positive 50 newtons. And then we add on 60 newtons, but it's in the negative direction. So I'm going to say negative 60, which ends up being negative 10 newtons, or 10 newtons to the left. And can you see here then that this black arrow also represented 10 units, and it was also pointing to the left.